Hello, and thank you for coming to watch my presentation. My name is Shreya Bangara, and this summer I conducted research for the SULI program at PPPL, investigating permanent magnet mirrors. I worked under the mentorship of Sir Stephen Cowley. First, we'll give a brief overview of my talk. I'll walk you through my motivation and goals for the project. Then we'll delve into some background on magnetic mirrors. We'll explore my derivation of analytical solutions for permanent magnet mirrors and walk through some other possible mirror configurations. We'll end with some concluding remarks. Now, you all know about permanent magnets. They're what have been holding your drawings up on a grid since childhood. But I want to convince you that permanent magnets are capable of so much more than that. In fact, they may help us achieve nuclear fusion. As we move into an era of clean energy and renewable sources, it's important that fusion needs to be accessible so the entire world can move forward evenly. Unlike electromagnets, especially those made with high-temperature superconductors, permanent magnets do not require power supplies or cryogenic cooling. They are conveniently adjustable, demountable, and low cost. I'd like to propose that they could possibly be used to make fusion cheaper, but also in a wide variety of applications as well, ranging from confining fusion accelerator devices to cheapening medical imaging devices such as MRIs. My goals were to investigate permanent magnet technology as a simple and accessible option for fusion mirror configurations. I wanted to demonstrate magnetic mirrors with field maxima of 4 Tesla using neodymium boron iron permanent magnets. I wanted to design realistic devices and generate overarching manufacturing plans as well. I worked on deriving the spherical analytical solutions for permanent magnet mirrors and expanded those to a variety of different configurations. I'd now like to dive into some background on permanent magnet mirrors. A magnetic mirror consists of 2 symmetric opposing magnetic structures. The magnetic lines in between trap charged particles which gyrate around the lines and undergo periodic motion between the 2 structures. As demonstrated in this lower image, the end magnetic structures are usually generated by coiled electromagnets, with plasma confined in the chamber and the magnetic field within. I'd like to propose that we can use permanent magnets for those end coils instead. Now we have our overarching question. Can we replace the coils on either end of a magnetic mirror with permanent magnets instead and still achieve good mirror configurations? Well, let's break down the steps. Where do we start? We'll begin with 2 blocks of permanent magnets. We choose to explore a hemisphere block with an inner cutout of another smaller hemisphere inside. Now we have these blocks of permanent magnets. How can we arrange the magnetization within these blocks to maximize the field at the center of the inner sphere? We start by deriving the field from each differential element of magnet inside those hemispheres. We calculate the maximum magnitude of magnetization using the remnant field and the size. We then evaluate the magnetization of each dipole that maximizes the field at the center within the hemisphere of the mirror from each differential volume of magnet. Essentially, for each little chunk of magnet inside the mirror, we want to orient the dipole such that the magnetic field is maximized at the center. For next steps, I'll first describe in farther, broader senses, and then we'll dive into the details. To evaluate the field outside of the magnetic structure itself outside of the hemisphere, we then integrate over the volume of the magnetic structure and evaluate the magnetic field at all points outside of the hemisphere. This plot here demonstrates a magnetic field outside of a hemisphere with inner radius 0.1 meter and outer radius 1 meter. You see that the magnetic field is strongest at the center, goes outwards, but as we move up the edge, the magnetic field starts to curve back in. To determine the overall mirror field between the two hemispheres, we can sum the symmetric fields of the two and develop our magnetic mirror. For instance, in this case, we see the field lines that arch from one mirror device to the next, trapping charged particles in between. I've derived the analytical solution for the field, the maximum field at the center of the hemisphere cavity, which is dependent on the ratio of the inner and outer radii of the hemisphere. The equation itself is outlined here in red. See, it depends on the natural log of R in over R out at the center of the field. We are able to achieve field of over 4 Tesla as demonstrated in this graph, where the outer radius is locked at 4 meters, and the inner radius varies from 0.05 to 1 meters. In addition, in general, we're able to sustain fields of more than 1.5 Tesla, even with very feasible ratios of radii. Now, we derived this expression for just a hemisphere, but what if we wanted to explore different mirror configurations and different geometries? Well, let's break it down. The 1.38 number is dependent on the limits of the phi integration. If we wanted a different sort of spherical shape, then that factor would change very easily. This division by 2 depends on the fraction of the solid that we're taking the mirror to be. The hemisphere is 1/2 of a sphere. If we wanted to use more of that sphere, we would change this factor. Finally, this natural log of the radii depends on the radii being constant. If instead they were dependent on phi of theta, that factor would evaluate to a different metric. Therefore, depending on the different sorts of resources and the area available and the maximum field that we want to achieve, the different parameters of the mirror can be chosen and easily substituted within this expression, reevaluated to determine the mirror configurations that best achieve our requirements. Now that's the field just at the center of the hemisphere. What about the field everywhere else within the mirror? That's important to us as well. To determine the field within the entire mirror, we integrate across all of our optimized dV differential elements of permanent magnet with respect to points outside of the field. Now, as demonstrated here on the right, this is the analytical solution just for the Z component of the magnetic field for some point outside of that hemisphere. It's quite complex to solve. Therefore, I harness numerical methods of integration to calculate and approximate the magnetic fields within the mirror. I developed a code base to take in various and diverse sorts of mirror configurations and geometries, different parameters, and different areas of field to evaluate, and can generate magnetic fields for all of these situations. This code base will be very helpful moving forward in actually taking these theoretical mirror configurations and determining which are usable and acceptable for our different requirements and needs. Now we'll explore some mirror configurations that I looked into throughout my project. The most basic is our hemisphere configuration with our outer radius demonstrated here and an inner radius with a smaller hemisphere cut out. I also looked at an ellipsoid, which simply has a smaller ellipsoid cutout, and a Pac-Man shape, which is 3/4 of a sphere with an identical cutout in the center. Now the hemisphere is simple, symmetric in all directions, and easy to calculate. The ellipsoid is a little more computationally intensive. However, if the situation allows for greater depth in one dimension, it's a great way to increase the maximum possible magnetic field without utilizing significantly more amount of magnet. The Pac-Man configuration is great if the space is limited, but a very strong field is still desired because we can pack more magnetic material into the same volume. However, it does decrease the size of the plasma chamber able to be sustained within the nerve, as the overarching hang-offs from the Pac-Man mouth constrain the volume of a chamber that can fit in between the two Pac-Man shapes. I investigated various manufacturing plans for these magnetic mirrors, as high-level advanced magnet manufacturing with custom fields is rather difficult and tricky. One option is to approximate the hemisphere and spherical solutions with a truncated icosahedron. In this case, we can use casting, so the same casting, to create these hexagonal and pentagonal and hexagonal pyramids or slivers of the sphere. Now, it's important to realize that the dipoles are actually identical and symmetric all up and down each of these slivers, meaning that the entire pyramid can be magnetized together and at once. This drastically cuts down on the time and cost of manufacturing. Another option, as demonstrated on the right, is to divide the mirror into slices like an orange, then use additive manufacturing and magnetize layer by layer of the material as it's put down. In conclusion, I would like to propose that permanent magnets can be used in magnetic mirror confinements. They can be used to sustain quiet fields greater than 1.5 Tesla, and even fields in the vicinity of 4 Tesla. And they could be used for plasma confinement. My next steps would very much focus on determining the most appropriate and most fitting configurations for use cases at PPPL, and determine what kind of manufacturing and assembly methods would work best. Do these slivers of magnet, if we use a truncated icosahedron option, do they come together when we assemble and naturally attracted to each other, or is there another step we need to take to put them together? How are we going to design the plasma chamber in between? And what kinds of manufacturing techniques even exist at the advanced magnetics level? In addition, the magnetic fields being able to be sustained by permanent magnets could possibly be used in medical devices where a large magnetic field is necessary, such as MRIs, so often very high cost and not available to a lot of developing regions. I would like to very much thank my mentor, Sir Stephen Cowley, for being always enthusiastic and available and a great role model for me. I'd like to thank everyone who made SULI possible, in addition to the graduate students, researchers, and professors who made me feel like SULI was a second home. I very much enjoyed my time in this program, and I'm very thankful that I've had the opportunity. With the side my image references, and thank you very much for watching my presentation. Please feel free to leave comments in the comments doc attached. Thank you.